ชมนิทรรศการอยู่รายการของเราจะเริ่มเวลาบ่าย2 โมงตรง 14 นาฬิกาตรงนะคะ14 นาฬิกาตรงจะเป็นการกล่าวต้อนรับโดยอธิการบดีจุฬาลงกรณ์มหาวิทยาลัยรองศาสตราจารย์ดร.พิชัยสมฤทธิ์จากนั้นจะเป็นการอ่านสารจากอดีตนายกรัฐมนตรีและประธานคณะกรรมการที่ปรึกษาไทยของงานสารสัมพันธ์สู่สันติวัฒนธรรมในอนันต์ปัญญารชุนอ่านโดยประธานกรรมการบริหารมูลนิธิสันติภาพนานาชาติมิสเตอร์อูเวอร์มอร์เวตจากนั้นเป็นการกล่าวต้อนรับโดยผู้อำนวยการฝ่ายอาวุโสของธนาคารกสิกรไทยดร.อดีตนายชุนไทยนะคะหลังจากนั้นแล้วก็จะเริ่มเข้าสู่รายการบรรยายโดยศาสตราจารย์ดร.พอล เจค ครูเซนโดยที่จะมีการแนะนำประวัติของท่านอย่างสั้นๆค่ะOur program special lecture within 5 minutes. You are requested to close the mobile phone, and in case you would like to ask a question, you can write down a question on a piece of paper that we provide for you. ต้อนรับอย่างเป็นทางการอีกครั้งนะคะเข้าสู่รายการแสดงปาฐกถาในรายการสารสัมพันธ์สู่สันติภาพในเรื่องมลพิษทางอากาศในเอเชียและผลกระทบต่ออุณหภูมิและชั้นบรรยากาศโลกเรื่องช่องโหว่โอโซนในบรรยากาศชั้นสตราโตสเฟียร์ความไม่เสถียรของสารเคมีในบรรยากาศที่เกิดจากกิจกรรมของมนุษย์และเราจะเรียนรู้ได้อย่างไรสำหรับรายการของเรานะคะก็คงจะเริ่มต้นด้วยการกล่าวต้อนรับและจากนั้นถึงจะเป็นการบรรยายโดยโปรเฟสเซอร์ครูเซนค่ะและขออนุญาตที่จะดำเนินรายการเป็นภาษาอังกฤษเพื่อเป็นเกียรติกับโปรเฟสเซอร์ครูเซนค่ะ Good afternoon, distinguished guests, ladies and gentlemen. From now on, about 20 minutes past 2 is donated to welcome speech for the special lecture of today, which we have the great honor from Nobel Prize Professor Dr. Paul Crutzen. Auspicious time now has come. May I have the honor to invite President of Chulalongkorn University, Professor Dr. Pichai Sumit, to deliver welcome speech. Please, Dr. Pichai.
Professor Paul Crutzen, Mr. Uwe Morawetz, Chairman of the Board of Directors of the International Peace Foundation, Dr. Adit Lai Chu Thai, representative of Kasakorn Bank, ladies and gentlemen. On behalf of Chulalongkorn University, it is my privilege and pleasure to welcome Professor Paul Crutzen, 1995 Nobel Laureate for Chemistry, and all distinguished guests attending the third lecture in Chulalongkorn University's series, Riches Dialogues Towards a Culture of Peace today. I cannot help but reiterate how honored we are that Chulalongkorn University is lending its collaboration to the National Peace Foundation in hosting the aforementioned series of activities here in Thailand. The lecture we are presenting today, The Stratospheric Ozone Hole, a man-caused chemical instability in the atmosphere, what to learn from it. Co-hosted by Kasakorn Bank, is only one of a series of over 100 lectures and dialogues, seminars, workshops, and place in the coming months. Following last week's lecture by Nobel Laureate for Chemistry, Professor Jerome Carr, is yet another distinguished recipient of the prestigious award, Professor Paul Crutzen. We are anticipating more stimulating and thought-provoking lectures with the presence of other Nobel laureates in peace, physics, chemistry, and literature, as well as decision makers in international politics, economics, science, culture, and the media. We hereby acknowledge not only the opportunity to welcome a world-renowned Nobel laureate to our country, but also the occasion for fellow Thai scientists and educators from various educational institutions to avail of the chance to be inspired by their expertise and insight. A person who has devoted his entire career in pursuit of progress and development in science. Professor Paul Crutzen's lecture today will focus on the vital role of science and technology in relation to such areas as quality of life, global environment, natural resources, politics, and the world economy. The title of his lecture is perhaps most aptly phrased in the form of a question: what to learn from it? And is thus applicable to so many more relevant and interconnected topics. I am confident we will have a lot to ponder from the series of lectures brought to us by the International Peace Foundation and Kasikorn Bank during the course of next year, as well as from today's speech of Professor Paul Crutzen.
All time is still donated to welcome speech. For the next message will be the message from former Prime Minister and Chairman of the Thai Advisory Board for dialogue toward a culture of peace. That will be read by Chairman of the Board of Directors of the International Peace Foundation, Mr. Uwe Morawetz. May I have the honor to invite Chairman of the Board of Directors of the International Peace Foundation to read the message. Please.
I am pleased to introduce you to the event series Bridges, Dialogues Towards a Culture of Peace, which the International Peace Foundation hosts in partnership with various national and international organizations, institutions and enterprises in Thailand. At the events, Nobel Laureates for Peace, Physics, Chemistry, Medicine, Literature and Economics, and other personages in the fields of international politics, economy, science, culture and the media will join hands with distinguished Thai leaders to promote the kingdom as a center for dialogue and international understanding. To achieve best results, each of them will stay in Thailand for several days. This means that within a period of 6 months and 80 actual event days, more than 100 lectures, seminars, workshops, conferences, and major public events will be held. With a Nobel Laureate or other dignitary coming to Thailand about every week, a deep and ongoing dialogue process towards a culture of peace is guaranteed. In addition, well-known performing artists lend their voices for the promotion of peace and non-violence to inspire a general audience and the young generation. The multidisciplinary and pluralistic approach of the events program reflects that peace involves all parts of society. It involves awareness and social responsibility of politicians, the business community, scientists, artists, and the media. And since peace within ourselves, our families, and our environment starts in our minds and hearts, it involves every one of us. In this sense, Bridges, dialogues towards a culture of peace, invites us to cross borders and build bridges by listening and opening up to other viewpoints, by generating new thoughts, and by developing innovative forms of cooperation. This can lead us to a world in which we will be able to understand each other and the complexities and challenges we face today in a new light. The globalized world needs broad strategies for change to secure a sustainable future for us and the next generations. Let us there be inspired by the knowledge and wisdom that Bridges dialogues towards a culture of peace promises to provide. His Excellency Anand Panjarachun, former Prime Minister and Chairman of the Thai Advisory Board for Bridges, dialogues towards a culture of peace.
For the series of welcome address, it will go forward to welcome remark by Senior Vice President of Kasikorn Bank, Dr. Adit Lai Chutai. May I have the honor to call upon Dr. Adit Lai Chutai to deliver the speech as a welcome remark, please.
Honorable Professor Paul Crutzen, President of Chulalongkorn University, Chairman of the Board of Directors of the International Peace Foundation, distinguished guests. In celebration of humanity without borders and in admiration of Thailand as a peaceful country, Kasikorn Bank is proud to sponsor speeches by 22 different Nobel laureates. For the next 2 years, each Nobel laureate will deliver his or her keynote addresses in Thailand as part of the International Peace Foundation's Bridges Dialogue Towards Culture of Peace project. On behalf of Kasikorn Bank, I'm honored to present Professor Crutzen, the winner of Nobel Prize for Chemistry in 1995. Thank you.
Distinguished guests, ladies and gentlemen, may I have the honor to bring you all close to Professor Paul J. Crutzen again. Professor Paul J. Crutzen received Nobel Prize in Chemistry in 1995 for their work in the atmospheric chemistry, particularly concerning the formation and decomposition of ozone. That is, our salvation from the global environmental problem that could have catastrophic consequences. The ozone layer, the ability small but big point of the atmosphere. Professor Crutzen has started his academic study with civil engineering and further his study in science for master's degree and doctorate degree. He began the first work as civil engineer at the construction bureau of the city of Amsterdam, the Netherlands. All this time, he had longed for academic career. The first academic career started with computer programmer at the Department of Meteorology, Stockholm University, Sweden. Basic competence received a special art for programming computer language in specific machine code. Forward him, the world leading researcher in mapping the chemical mechanism that key the ozone content. time, he worked as a computer programmer. He was assigned to help a scientist from the US to develop a numerical model for an oxygen allotrope distribution to atmosphere. You can call this point as an initial condition for him to start as a scientific career. Because from this project, photochemistry of atmospheric ozone has sparked his academic interest. Professor Crutzen himself stated with a great determination that I want to do pure science related to a natural process. 30 years after initial condition of scientific career in 1965 to assist a scientist, he received a Nobel Prize in Chemistry in 1995 for identification of nitrogen oxides as catalytic converter of ozone in the stratosphere, a phenomenon that depletes the ozone layer. At the point he picked the answer for ozone hole phenomenon, surprisingly, it's on the way he flew back from an ozone hole workshop to Germany with unpleasant an explanation for ozone hole phenomenon. Why he had hardly sleep, difficulty to sleep on the transatlantic flight. He got a good time and suddenly he realized that oxide of nitrogen play a major role for ozone hole phenomenon. On the track of his scientific career, his success in atmospheric chemistry without background in chemistry. He is a chemist by training because basically he compiled and comprehend much of neat chemistry by himself from a valuable publication. He can read much more, partly because of his language proficiency in French, English, and German. In addition, he himself has integrated mind because he likes playing chess as a third sport and reading varieties of books such as Travel in Distant Lands, Astronomy, as well as Bridge and Tunnel. And from his lecture, Nobel lecture in 1995, Professor Crutzen said, I inherited a cosmopolitan view of the world. My mother's parents were of mixed German and Polish origin. My mother worked in Amsterdam where she met my father. My father comes from a little town in the southeastern corner of the Netherlands, bordering Belgium, Germany. And he had relatives in the Netherlands, Germany, and Belgium. In addition, he mentioned in his lecture that his wife, who always brings happiness as a center of family in happiness all the time. His wife, Chulalongkorn, is Finnish, who studied history and literature at the University of Helsinki, Finland. Among the huge award and honor he received through his life, some of that signify his path in intricate study and multidisciplinary approach. For example, in 1976, he received the Outstanding Publication Award from National Oceanic and Atmospheric Administration. In 1985, he received the Laureate Award for Physics in the Public's Interest. In 1995, he received Nobel Prize in Chemistry and the Global Ozone Award for Outstanding Contribution for Protection of the Ozone Layer. And for the year just passed, 2002, he is the worldwide most cited author in the geoscience, with 2,911 citations from 110 publications during a decade. Professor Crutzen, you are our role model in way of life. Determination time, strong and brave determination have integrated mind, open mind, and multidisciplinary approach. We can notice that from the first job involving in brick construction in 1954 until now, half-century past, Professor Crutzen is constructing a brick again, but constructing nationwide brick to cover the whole of ozone. So, may I have the great honor to invite Nobel Laureate Professor Dr. Crutzen to deliver the public lecture on the stratospheric ozone hole, a man-caused chemical instabilities in the atmosphere. What to learn from it? Please, Professor.
Excuse myself for taking a picture, but this is such an important occasion that I need to have a memory of this. Thank you very much for your kind introduction, Professor Morawetz. I also would like to thank the President of the University, Professor Tachai, and the donor, so to say, of this trip to Thailand, Dr. Adit. And not last but not least, I would like to thank Uwe Morawetz for his invitation and his hard work for peace. I will tell you a little bit as already indicated. Do you need to stay there or? Okay. I would like to give you an overview of the chemistry of the stratosphere. I have to start by saying that when I got interested in the chemistry of the atmosphere at that time, that was about 35 years ago almost, everybody thought that there were no problems, that we knew everything about the chemistry of ozone in the atmosphere. Things were so simple that one believed at that time that to explain the distribution and the concentration of ozone in the atmosphere, one only needed to know 4 reactions. And let me see which knob. No? This one. Somebody has to. Oh. Yeah. There we go. So, I was looking. Let's first have a look at the composition of the atmosphere. This is given here. We have oxygen, 21% almost. That's very important. We breathe it. We have nitrogen, 78%. It's almost a neutral compound in the atmosphere. It doesn't do very much, except in the form of nitrogen oxide. We'll come to that. And we have argon, almost 1%. If you add up these numbers, you get 100%. So you may get the impression that there is not much more in the atmosphere. But it turns out that these minor constituents, which are available in the atmosphere, they are of the greatest importance to explain our climate and also the overall chemistry of the atmosphere. Nitrogen, oxygen, and argon cannot be influenced by human activities. They change. Nitrogen, oxygen can change over time periods of millions of years, but not in the lifetime of human beings. But the minor constituents in the atmosphere, they can change. And we have examples, carbon dioxide, CO2. Of that compound, we have 360 per million molecules in the atmosphere. we call it 370 parts per million in the atmosphere, and that is a compound which is growing in the atmosphere. And the growth of carbon dioxide in the atmosphere we are concerned about, because carbon dioxide is a so-called greenhouse gas which warms the Earth. And with more carbon dioxide in the atmosphere, we get an increase in temperatures. And with that increase in temperatures, we can also have sea level rise and problems about which I will talk this evening at the Foreign Correspondence Club. And I hope some of you will find the time to come there. Now, there are even compounds in the atmosphere with much lower concentrations in carbon dioxide, like methane, CH4. Of that we have only some 1.7 molecules per million air molecules in the atmosphere. So a very minor constituent. It plays a role in Earth's climate. In other words, it's a greenhouse gas. But it also plays a role in the chemistry of the atmosphere. And then we have ozone. The chemistry of the atmosphere is very much determined by ozone. And I can only cover in this lecture the importance of ozone in the stratosphere, but it turns out also low down at the Earth's surface that we can have the so-called photochemical smoke ozone. So the chemistry of the atmosphere, the cleaning of the atmosphere from whatever we put into the atmosphere or what nature puts in the atmosphere is very much dependent on the availability of ozone in the atmosphere. And maybe some of this I can speak about in the evening elsewhere during this lecture series. Of ozone we have variable amounts. If we have air pollution at the Earth's surface, we can have 100 per 1,000 million air molecules in the atmosphere. We can have 100 parts per billion, we call that. Or in the stratosphere, we can have 10 parts per million of ozone. And it's extremely important compound which I will come back to. Nitrous oxide has even lower concentrations, 0.31 parts per million in the atmosphere, but it plays a large role in the chemistry of the stratosphere, and also nitrous oxide is a greenhouse gas. And then we have these famous CFC gases, chlorofluorocarbon gases, which have even much lower concentrations in the atmosphere, less than 1 parts per 1,000 million, 1 part per billion in American units, let's say. So and all these compounds have been or are changing in concentration in the atmosphere. Now, what we show here in this view graph is the distribution of ozone in the atmosphere. You see up to about, in the right-hand scale, you see the height in the atmosphere. In the troposphere, up to about 10, 12 kilometer altitude, we have very little ozone. But it's very important for the chemistry of the atmosphere. But again, the time is too short to say much about that. In the troposphere, now you see another curve there called T, that's the temperature. Temperatures decline with height in the troposphere. In the stratosphere they are constant. And that means, because we have these constant temperatures with altitude, that the stratosphere is very layered, it's very stable against vertical mixing. And that is why ozone can build up in the stratosphere. And that is good, because if that would not be the case, then much of the ozone which is created in the stratosphere would make it down to the Earth's surface, and that would be a very bad atmosphere. So it's good that we have this temperature conditions in the atmosphere with constant temperatures in the stratosphere, because without that we will have lots of troubles at the Earth's surface because of too much ozone. But nature has made the atmosphere in such a way that we have these favorable conditions. Now, ozone is important because without ozone in the atmosphere, and most of it in the stratosphere, 90% of all ozone is in average in the stratosphere, without that, all radiation with wavelength longer than about 200 nanometers, that's the lower scale, would be coming down to the Earth's surface. And that would make life as we know now on Earth totally impossible. only in very hidden compartments in the biosphere there are bacteria and species which can survive with this ultraviolet radiation, but certainly not human beings, not even in Thailand, although you have brown skin and people like me. So between 200 and 300 nanometers have shown the wavelength of the radiation, solar radiation. Ozone is absorbing the ultraviolet radiation, and in that way it is a filter against ultraviolet radiation. And that is of course very important. At shorter wavelength, other gases can do the job, like oxygen and nitrogen. But then the absorption is already happening much higher up in the atmosphere, which can read in the left scale. Now, when I started my studies in Stockholm on ozone, there were only 4 reactions one really had to know, and they are listed in the right-hand corner of this view graph. These reactions were invented and proposed by Chapman, a famous atmospheric scientist, in 1930. And the reactions which were listed are shown here. The photolysis of oxygen, O2, makes oxygen atoms, 2O, at wavelength, solar radiation at wavelength less than 240 nanometers. That creates 2 oxygen atoms, and each of those combined with oxygen to make ozone. If you add that up, out of 3 oxygen molecules, 2 ozone molecules are created. Now we also need reactions to go the other way, because otherwise, in 1,000 years, all oxygen in the atmosphere would be converted into ozone. And we don't like such conditions, and therefore it is good that there are reactions which destroy ozone, and they are given below. And so unfortunately at this view graph an error has taken place because one reaction is missing. Ozone with a photon creates O plus O2, you can read it there, and then some of these O atoms which are created there react with ozone to make 2 times O2. And in other words, out of 2 ozone molecules we form again 3 oxygen molecules. And these systems, production and destruction, are in balance. And one thought that these are the only reactions which are important. But however, very detailed work by Benson and Axworthy showed that the reaction rates which were used by Chapman and all scientists basically until the end of the 1960s, that these reaction rates were wrong. In other words, if one takes the right reaction rates, one gets ozone profiles which are listed then in the figure in the right-hand side. You see there are 4 curves there corresponding to various latitudes, but you see one set of curves, the right, is what you would get from the Chapman reactions. Well, in reality, you get the curves which are to the left. So when this came about, we started thinking about possibilities. Maybe there is a possibility that additional reactions come into effect. Now, maybe that's important because the Chapman reactions, they are totally natural reactions. They cannot be influenced by mankind. They are dependent on the influx of solar radiation in the atmosphere and the availability of oxygen. But mankind cannot influence that. However, if we, I just told you, we knew that additional reactions are needed, and they are listed in this view graph. We have again in the top corner the top 3 reactions, the reactions making ozone, and then the Chapman reactions below that, and then it turns out that additional reactions are needed, and these reactions are in the 3rd place on this view graph. They involve some compound X, let's call it X for a while, reacting with ozone. You get then XO and O2. The O atoms, which are created by photolysis of ozone, react with XO to make X and O2. And if you add that up, you get out of 2 ozone molecules 3 oxygen molecules. But you see, in these reactions, catalysts, X and XO, play a role. They do get things going and additionally destroy ozone. And these catalysts can be influenced by human activity because that X can stand for NO, nitric oxide. And nitric oxide is produced by the oxidation of nitrous oxide, which is N2O. And N2O is coming from the application of nitrogen fertilizer at the Earth's surface. That creates then a flux of N2O in the atmosphere, and that N2O gets into the stratosphere and produces NO, which then catalytically destroys ozone. In that way, human activity can influence ozone. And X can also be chlorine atoms. And chlorine atoms come from the chlorofluorocarbon gases. And it turns out that the main influence of human activities actually came about because of the presence of the chlorofluorocarbon gases, the CFC gases in the atmosphere. And this is something which was proposed by my colleagues who shared the Nobel Prize with me in 1974. Now, very quickly, there was a natural experiment performed in 1972, August 1972. A solar proton event took place. The sun became very active and in a few hours' time emitted protons from its surface into the interplanetary space, and some of these protons reached high latitudes on Earth. They are deflected by the electromagnetic field of the Earth. So these protons come down on Earth at high latitudes, above 65 degrees north or south of 65 degrees south. And in these few hours, NO, nitric oxide, was produced, and those are the 2 curves. Is there a pointer here by any chance? Well, if not, I just continue by saying. But you see 2 curves in the full lines, indicating the amount of nitric oxide which was produced in these few hours of times. And in the stipple curve, that's the normal amount of NO in the stratosphere. And you see that, for instance, at 40 kilometers, we doubled in a very short period of time the amount of NO in the stratosphere, doubled. And if that happens, if our theory is right, then ozone should be depleted due to this solar proton event. And in fact, once we have indicated this possibility, our colleagues of the National Astronautical Association in NASA in the United States, they analyzed the data, and what they found is in the red curve what was measured, and in the other curves what was predicted by theory. And you see that these curves come very quickly together. What it shows is the percentage depletion of ozone, say a week after this solar proton. So this was a confirmation that indeed our theory regarding the nitrogen oxides was correct. And that was important because we had a hypothesis but no proof. Let me go on a little bit here. Now, the CFC gases, most of my talk will be concerned with the CFC gases. They are produced especially in the northern hemisphere, at mid-latitude in the northern hemisphere. But their lifetime in the atmosphere is very long. So once they are emitted, even in the northern hemisphere, at high or mid-latitudes, they reach everywhere around the world, because the lifetime is 40 years, and the winds and the turbulence in the atmosphere will spread them into the southern hemisphere. For instance, here we have data of the chlorofluorocarbon 11 and 12 as measured in Tasmania, and you see up to 1987, the measurements show an increase in the CFC gases in the atmosphere by of the order of 5% a year, which is a large increase from year to year, 5% more and more. So this is data from I hope I can't see it myself, sorry. But anyhow. Good. I have to do it without because I can't see the red spots. It's there, but my eyes are not good enough for it. Sorry. Well, anyhow, we see that the CFC gases reach the other hemisphere, and in fact also, of course, reaches the stratosphere. Now, these gases, we know they did not exist in the atmosphere before under natural conditions. And why do we know that? We can analyze air which is trapped in glacier ice, and we can look for the chemical composition of that air, which was enclosed, say, hundreds of years ago. And when you then go deep enough in the ice, you will find that, for instance, the CFC gases were there. We saw them increasing with height towards the top of the glaciers. So you see this for the CFC gases. So they have no natural sources. They have just the industrial chemical industry as the source for the CFC gases. My colleagues have pointed out the danger which was concerned with the presence of the CFC gases in the atmosphere. We had to confirm their theory too, not only the nitrogen oxides. And measurements were made of the composition of these circles and squares are data indicating as a function of altitude on the left scale the concentrations of the CFC gases in the atmosphere. And you see they very quickly above about 20-25 kilometers go down with altitude, and that is due to the destruction of the CFC gases in the stratosphere. And during that destruction, chlorine atoms are formed, and the chlorine atoms together with chlorine monoxide destroy ozone. These are the ozone killers, you can say. And you see that the full drawn line are theoretical calculations, and the other points are measurements. So very good correspondence between observations and theory. Good. So we felt that we knew a lot about the chemistry of the stratosphere, especially at the end of the 70s. And even the concentrations of chlorine monoxide molecules, one of the ozone killers, actually has been measured as a function of altitude, with the scale again here, 35 kilometers for instance here. And we have also the concentrations in the atmosphere. And look here how small the concentrations are, between 10 to the minus 10 and 10 to the minus 9. So very low concentration. But still, these compounds are very dangerous because they act as catalysts. Once a chlorine atom is added to the stratosphere, it keeps circling and destroying ozone 10,000 times before it is finally removed from the stratosphere. So one molecule of CFCs can destroy more than 10,000 molecules of ozone. That's why we have this problem with these gases. Now, the theory and observations look very similar, so we thought we understood the chemistry of the stratosphere. But let's go further. What we understood very well was actually the chemistry of the stratosphere in above about 25 or 30 kilometers. These are curves. We look here at the percentage depletion of ozone as a function of altitude in kilometers, and we see that in 2005, for instance, if that the predicted depletions of ozone in the year 2005, and we are very close to that, should have been of the order of 25%. And that's about right. What we calculated at that time with regard to ozone depletion about 25 to 30 kilometers was certainly correct. We thought also that at lower altitudes not much would happen to ozone. And one of the reasons is that the ozone killers kill each other. The CLO radical and NO2 molecules, both of them individually destroy ozone in catalytic reactions. But they also destroy each other, making chlorine nitrate, or in other reactions, hydrogen chloride, and they don't react with ozone. So in that way, ozone is protected from stronger destruction than indicated. So we thought that this was the situation, this was our scientific understanding, and we were quite proud of ourselves having come that far. But then, then a big surprise came. Our colleagues of the British Antarctic Survey measured over their station in Halley Bay for the month of October, that's springtime in Antarctica. They measured as a function of the year, they measured a very rapid decline in ozone. Now this is so clear that we don't need strict statistical analysis. This is just a very rapid depletion of ozone taking place, getting worse basically from year to year with some interruptions. This was a big surprise. It was such a big surprise that our colleagues of the British Antarctic Survey waited a number of years before publishing these data because they were afraid that these data were wrong. Because this was so unexpected that over Antarctica, the furthest away of the input of the CFC gases in the atmosphere, that we would just over Antarctica find the strongest ozone. Well, it turned out these measurements were correct. And what we also found out, the measurements of colleagues, is that exactly, if we now look at the vertical profile of ozone in the atmosphere, that exactly in the height region between, say, 12 and 22 kilometers, where we normally have an ozone maximum, just exactly there ozone is gone. That's the so-called ozone. Not predicted, I would say unpredictable. Anybody who would have predicted that, I think, at that time, would have been declared not being treated very well. Basically an impossible thing. So we needed an explanation for what was going on. It was clear that our understanding of the chemistry of the stratosphere was incomplete. And we got many theories which were developed, some even funny, that the extraterrestrials were cooking up the ozone layer. Some of the scientific theories which were developed were as bad, but not as funny. But finally, because of international collaboration between scientists from the United States and also from Europe, we found out what was going on. It turned out that beautiful clouds, which occasionally form at high latitudes, especially over Antarctica, the so-called mother-of-pearl clouds, they are produced at altitudes between 10 and 25 kilometers in the atmosphere. They're really beautiful. That these clouds, in the presence of large amounts of chlorine in the stratosphere, large amounts coming from the emissions of CFC gases, they become very dangerous. Because what is happening is that on the surface of these particles, and I will show this rather quickly, but the real meaning of this, I will say in words, on the surface of these particles, the nitrogen oxides, NO and NO2, are removed converted into nitric acid, HNO3. And HNO3 freezes out on the ice particles. And that means that one of the ozone killers is gone. And that the chlorine monoxide radicals, which are the other ozone killers, that they no longer are neutralized in their activity by the nitrogen oxide. So they are happy. Their enemies, so to say, are gone. And they then together act to destroy ozone. And furthermore, it was found out that the molecules which are formed normally in the stratosphere, chlorine nitrate and HCl, these molecules react with each other on the surface of these ice particles. They cannot do that in the gas phase. They do it in the surface of these ice particles. Nitric acid is formed, and that freezes out if temperatures are low enough, below about minus 80 degrees Celsius. And also chlorine molecules, CO2, are formed, and they photolize very quickly into chlorine atoms. And these chlorine atoms act then in a catalytic chain of reactions with the net result that 2 ozone molecules are converted into 3 oxygen molecules. And note here that this is dependent on the reaction of CLO with itself, that drives the speed of this reaction. And because the chlorine content of the stratosphere is increasing by 5% a year, the destruction rate is increasing by 10% a year. So once ozone is starting to go down, it will go down very quickly from year to year, worse by 10%. And this was then also shown by measurements. And let's concentrate on the lower part of this curve. What it shows is ozone concentrations at an altitude around 20 kilometers. Measurements were made on a United States aircraft. Ozone concentrations north of a region, north of the Antarctic, where temperatures are relatively high, that means warmer than minus 80 degrees Celsius. They are not much affected by chlorine, because the amount of chlorine is very low. But as soon as we enter a region in the stratosphere where temperatures are below minus 80 degrees Celsius, you see that the amount of chlorine monoxide, ozone killer, has gone up, and at the same time ozone has gone down. And if you would have the measurements 1 week later, in fact ozone, there would be no ozone there. So our theory and measurements in the atmosphere finally came together, and there was no doubt that ozone depletions were taking place, mainly over the Antarctic continent. In addition to, because of the ozone depletion, also the temperatures went down in the stratosphere. You see here data from various periods. You see the lower curve here is from 1986-87 to 1995. Maybe at lower temperatures in the stratosphere than in the other years. And lower temperatures means more conversion of HCl and chlorine nitrate to ozone-destroying species. So that also helps in destroying ozone. So there are many feedbacks here which come together and all in the way of destruction of ozone. Now the normal amount of ozone in the stratosphere is provided by metal chloride, and of that we have about, nowadays, only about 15% of all chlorine in the stratosphere. So now the other industrial chlorine compounds are given by the other bits here, and that means that's about 85% of all chlorine in the stratosphere comes from human activities. And because of the dependence of ozone destruction on the square of the chlorine content, this means that nowadays the destruction of ozone in the stratosphere by chlorine is about 50 times larger than natural conditions. So that explains why ozone really is small. So these chlorine reactions don't play a major role in the natural stratosphere. That's more reserved for the nitrogen oxides. But they play a large role in the present stratosphere. You see here satellite measurements looking down on the Antarctic, and you see the pictures of the ozone hole getting worse from year to year. You see the color code here. In fact, nowadays we have of the order of maybe on average 100, 140 Dobson units in the stratosphere. 100 Dobson units is 1 millimeter of ozone to protect us from ultraviolet radiation. And that's now, in other words, we have the amount of ozone in the Antarctic ozone region is about 1/3 of what is naturally the case. The area of ozone depletion has also increased. In the beginning, the area was very small. That was in 1980. But you see with following years, 1984, 87, etc., the area of the ozone hole, covering the ozone hole, has increased with time. Now, if you would have very careful looking at data, you would already have seen that in 1981 we had a small night out in ozone. And that got worse from year to year, but we could in principle have discovered all of this already, say, in 1980, but we didn't look carefully enough at the data, and on top of that, ozone is very variable in concentration, so it was hard to find. With time, ozone was continuing to deplete. These were the data which were reported by the British colleagues, the British Antarctic Survey, but with time ozone has been going down even more in the month of October, as shown in this curve. Now, the conditions to create ozone depletion over Antarctica are very unfavorable, because over a long period, and this is given here the Antarctic winter, over a long period, the temperatures are below -80°C. This is the borderline between for the production of so-called polar stratospheric cloud, or these mother of pearl clouds. So for a long time, temperatures in the Antarctic are below this line. That is favoring then ozone depletion. Over the Arctic, it's a shorter period, but even over the Arctic, we are for some time, from year to year differently, below this magic line of -80°C. So also in the Arctic, we can have the beginning of ozone. Ozone hole, and that is shown here. First we have conditions over Antarctica. This is the normal ozone profile, and this is what you see in springtime when ozone has been depleted chemically in this region between 12 and 22 kilometers. Over the northern hemisphere, we have this is the normal profile. We have normally more ozone in the northern hemisphere and over in the Arctic than in the Antarctic. But even there we see a depletion of ozone, and actually the amount of depletion is almost the same as in this case, a little less. However, we start from higher concentrations, so the percentage change in ozone over the Arctic is less prevalent than over the Antarctic. I just jumped a few curves. Now with ozone depletion, we have conditions in which more ultraviolet radiation reaches the Earth's surface as a function of wavelength, and here we have the fluxes of protons. Now 1988 was a year when the ozone hole was not that pronounced, so this was the UV curve, but in 1990 the ozone hole was deeper. That means that we have much more ultraviolet radiation reaching the Antarctic surface than in 1990 and in 1988. So there is some variation from year to year. Now, it's exactly in the wavelength region where ozone is most sensitive to loss, to ultraviolet radiation is most sensitive to the loss of ozone. That's around 200 or 300 nanometers. Exactly there, the various biological species, here we've got the various bacteria are shown, but you can also put in a curve of the skin here, skin cancer, they all look similar. You get very strongly increasing sensitivity of ultraviolet radiation to ozone loss. It's mainly driven by the biological response. So that means that except in tropical regions, where we have only minor ozone depletions, and mid and high latitudes, on average we have ozone depletions, average over the whole year, of the order of 4% or more in the southern hemisphere or Antarctica, mid latitudes of the southern hemisphere, and similarly, but somewhat less pronounced in the northern hemisphere. That has biological consequences, and they are listed here. Increase in ultraviolet radiation means increase in cataracts, 0.6% ozone loss. This is data coming from the United Nations Environmental Program. Non-melanoma skin cancer, white humans are very sensitive to ultraviolet radiation, so up to a 3% increase in non-melanoma skin cancer per percent ozone loss. And plants are sensitive to ultraviolet radiation, and also marine ecology is sensitive to ultraviolet radiation. I don't want to read all these consequences here, you see it for yourself. So there are international measures unfortunately taken since 1996, CFC gases, and also various other gases like methylchloroform, CH3, CCl3, and halogens. These are gases which contain bromine, besides chlorine and chlorine. They are phased out. They are no longer produced, so that's good for the ozone layer. It will slowly recover. Various products are brought into business, in production. Those are the so-called HCFCs. These are like the CFC gases, but they contain, instead of one chlorine atom, hydrogen. And when they do that, they are removed from the atmosphere already mainly in the troposphere. They don't reach the stratosphere. So those are the replacement products. Methyl bromide will be phased out probably in the year 2005. It's used as a fumigant in agriculture, and there's still a debate going on now whether it's hope this day it will maybe a little bit delayed. So the conclusion is that it will be better. It's going to be better, but it will take some 40 years, maybe more, until most of the ozone hole will have filled up again. Because the lifetimes of the CFC gases are very long. For CFC-3, that's CFC-11, it's about 50 years, and in the case of CFC-12, it's 110 years. So first, by the middle of this century, the ozone hole will open. And I won't experience that, unfortunately, but some of the young people will do, and maybe you will hold a party on this period in the chemistry of the atmosphere. But there are some additional worries, and that is whether this delay might increase. Because of the increase of carbon dioxide in the atmosphere, the stratosphere gets colder. The troposphere, and the surface warms up, but the stratosphere will get colder. And that means the probability of ice particle formation will go up, more ice particles, and the possibility that more chlorine will be converted in the aggressive forms of Cl atoms and COO atoms. So it may take even a little longer than we thought. We see that in this curve that when we think about the troposphere, we have already reached we have the years here, we have already reached an maximum around 1995. Since then, the amount of chlorine has been going down very slowly in the atmosphere. in the troposphere. In the stratosphere, it takes a little longer because the CFC gases still have to be lifted up by atmospheric winds and turbulence into the stratosphere. That takes until 5 years. So in the stratosphere we have reached maximum chlorine content roughly at this stage. From now on, stratospheric chlorine content will go down. And will go down. With that we have a slow recovery of ozone. Now we have the various agreements which were signed. If there would have been their effect on the chlorine content of the stratosphere, if there would have been no regulations, then the amount of chlorine in the stratosphere would have keep going up to very high levels, much higher than we have at present. Under the Montreal Protocol, which was declared in 1987, implying a 50% reduction in the emissions of CFC gases in the atmosphere. Under that protocol, we would still have an increase of chlorine in the stratosphere to high levels, just up to later dates. But fortunately, we had a strengthening of the agreements, made it longer, still a beginning increase, and finally, Copenhagen and Beijing, these are the places where these conferences were indicated basically zero emissions. So very slowly we see here the return of the atmosphere to normal conditions, a decline of the amount of cooling in the stratosphere, recovery of ozone. But the effects on the biosphere and on excess skin cancer would have been following these curves, and you see we have delays here into the next century, because to develop skin cancer takes time. If you go into the sun, you don't get skin cancer immediately when you get there. But with age, the probability of developing skin cancer, especially in white people, will go up. It's the integrated dose which is really important. And that means that even under the Copenhagen Agreement, that's the present agreement basically, we still have the consequences of skin cancer maximizing in the year 2060, when the ozone hole will be gone. So it shows you that we are talking here about inputs in the atmosphere of compounds which have long lifetimes, and their effects have even longer lifetimes because they are integrated into the biosphere. Well, let's basically show this already. We see here for various compounds that the concentrations in the atmosphere are flattening off, going down. In the case of methylchloroquine, we see a clear decrease. There are some other compounds in the atmosphere which are increasing, both in the northern hemisphere, the red lines, and the blue lines in the southern hemisphere. And these are the replacement compounds, which contain hydrogen atoms, and which are mainly removed in the troposphere, but nevertheless have an influence on stratospheric ozone, although on the molecule level, much less than the original CFC gases. Well, let's finally let me say something about the nightmare situation which could have happened. Namely, I just mentioned to you briefly bromine. If instead of chlorine, the chemical industry would have produced bromine, and we didn't know in the beginning much about chemistry about these gases. It could also have been such that the chlorine chemistry would have behaved like bromine chemistry. Because in the early 70s, when all these theories about ozone depletion were sort of brought into the world, we knew very little about the chemistry of these gases. Industry had not studied the effect of these gases in the atmosphere. So it could have been such that the chemistry of chlorine could have been like that of bromine, or also maybe the industry could have produced bromine gases. If that would have been the case, we would have had a very catastrophic situation, because bromine in the stratosphere is already, you don't need ice particles for that. It's mainly in the form of reactive bromine atoms, bromine monoxide molecules, and HBr, and also HOBr. And they all are all involved in catalytic reactions destroying ozone. If that would have been the case, then already in the beginning to middle of the 1970s, around 1975, everywhere, and not only in the winter or springtime, everywhere we would have lost already half of all ozone in the stratosphere. It could have happened. It didn't happen. We were just lucky that we didn't build up to a situation like that. And I tell you that, but because one of the issues is also what should we learn from this experience? Well, what we should learn of this experience is that we can never be sure that we understand everything. I told you in the beginning, we thought we understood the chemistry of the stratosphere very well, and that most ozone depletion would take place around 30 kilometers. In fact, it happened below 30 kilometers by new reactions which nobody had predicted. And the other thing, so we scientists should be always on the watch, so to say, we should guard against maybe even unlikely events and see, because they may have large consequences. We should have an open mind about it, and we should study the atmosphere, its chemistry and physics, much more than we are doing. This is one of the lectures. The other important lecture is normally when scientific thoughts and influences of human activities are discussed, normally people think it won't be so bad. Well, in fact, it can be much worse. The effects of the CFC gases, as predicted by us originally in the 70s by Molina and Rowan, they had part of the story. In fact, things were much worse than that. So we don't always over-predict and overemphasize the impact of human activities on the atmosphere. We can also, we can under-predict what is really going to happen. And if you look at the very complex climate issue, where not only chemistry is playing a role there, but also the biosphere, and of course the physics of the atmosphere, cloud formation, so much more complicated system. Who guarantees us that the predictions we are making about climate changes are over-predictions? They may be under-predictions. We have to learn this. We don't have the answer. Very great uncertainties, but these uncertainties should not be taken to mean that we must wait until the scientists have discovered everything. We have to wait for that. We may have to wait a century, maybe too later. I thank you very much for your patience, and I hope that there will be good time for discussions and questions. Thank you.
From now on, it's time to open for questions. During waiting for listen to your lecture, one person came to me for the first question, very simple one: how to fall in love in chemistry?
Sorry, but
how to fall in love in chemistry?
What with chemistry? Well, the way it went is that originally I hated chemistry. In high school it was actually my worst subject because it was taught in a way that you almost had to memorize things, but there was no real understanding behind it. Well, I became interested in it because I and a few others made this discovery that things weren't right. It was believed that the theory of 1930 explained everything. In all the textbooks it was written, it is well known that. And I finally said, no, it's not well known that. There's things missing. And I started looking in what could it be, and invented some of the nitrogen oxide reactions and introduced those. This was almost the first, I had one paper before that published, but this was basically my very first paper, which I wrote on myself without any supervision, and I got it published, and it turned out that was a major discovery. And once you have that feeling of success, and once you get involved in looking at the processes, not just by memorizing, by understanding them, then chemistry becomes suddenly so much more exciting. And it has always fascinated me. I can maybe I can find you a graph. Yeah, this is where I started which is the theory of 1930 by Shepard. There were four reactions, if you change the date. This was all the chemistry of the stratosphere in 1930, and still until about 1970 it was generally believed this was the chemistry of the stratosphere. Well, no, this is the chemistry of the stratosphere. And several of these reactions and the consequences I just discovered. And once you are on the right track, one thing follows the other. And of course, you are very happy that you are on the right track, and it then invites you or almost forces you to work even harder thinking about the system. And then you get situations like this. If you now make models of the chemistry of the stratosphere, you have to consider all these reactions. If you don't consider them, your model is incomplete. In this graph, it's not the now I've forgotten which one to push. Anyhow, I do it. You see, the only thing we have added to the chemistry of the stratosphere is all these chlorine reactions, and one should also add bromine reactions. In the left upper corner, that is added by because of the input chlorine gas. Without that, all the other boxes are natural processes. And I think if we would not have put chlorine into the stratosphere, then still the chemistry of the stratosphere would have increased in complexity from the original Chapman reactions listed in the upper, almost upper right corner of this graph. OX, it says, O chemistry. We added in the hydrogen chemistry, the box below, and the nitrogen chemistry. That's the box on the left lower. Those are the natural reactions. You always, in addition, the chlorine reactions and bromine reactions. So this is maybe to look into a very complex picture, but once you have worked with it, it gets very fascinating. And all of that has to be treated together with the meteorology of the stratosphere. Because all of this is not just happening in a box in the stratosphere. No, many boxes, they move with the winds. They go down in the troposphere, they can go up in higher levels, and they can go to the north or the south. So we also have to consider meteorology and temperature changes. Temperature is so important because of the possibility of ice particle formation. And once that happens, you get additional chemistry, which happens on the surface. And all of that is new stuff compared to what was the case at the end of the 60s.
For the next question, or if anybody would like to ask Bio, please raise your hand for the microphone we provide for you too. For the next question from Patrick, oxide of nitrogen from automobiles emit and contribute air, especially during car park with engine on or heavy traffic. The amount of oxide of nitrogen would account for oxide of nitrogen contributed into our level of stratosphere or not?
Can you repeat it? Okay. Because of the echo, it's so hard to. So NOx from automobile emission contaminates. Oh, that's another story. Yeah. And it's an important story. The nitrogen oxides in the stratosphere, they destroy ozone above about 20 kilometers by the reactions which I've shown on the first slide, the second slide. In the troposphere, the nitrogen oxides NO and NO2 create ozone. In a mixture of hydrocarbons, methane, carbon monoxide, and nitrogen oxide, and sunlight, you produce ozone in the troposphere. So the role of nitrogen oxide is very complex. You can, in the stratosphere, adding NOx to the stratosphere will lead to the destruction of ozone above about 20 kilometers. In the troposphere, it adds to ozone.
The next one, why is the depletion of ozone in the Antarctic zone more serious than that in the Arctic zone?
Oh, good. The reason is that it's just much colder over the Antarctic than over the Arctic. So the probability of formation of ice particles on which reactions take place, which what we call activate chlorine to destroy ozone, they are much more active over Antarctica than over the Arctic. I showed this in one period in which ice particles can be formed in the stratosphere over the Arctic is mainly in say the month of February and March, while that's the beginning of springtime over the Arctic. While over the Antarctic you already at the beginning of the winter the temperatures are so low that you start this catalytic reaction which on the surface of ice particles which activate the winter. And also the period over which the ice particles can be formed, both periods last until October. And that is the period much shorter over the Arctic.
Did you find any difficulties to propose theory or hypothesis that totally different from the mainstream of belief for 30 years that you mentioned before?
Oh yeah, well, it's a good question. Always, not only in this case, but also other cases, when I have met, maybe I'm not very modest, but I mean, I have not only discovered the influence of nitrogen oxides in the stratosphere and troposphere, and but also I've been involved in other thoughts. And the thoughts I've had in my career are always really very simple. And the first question you ask yourself is, there must be something wrong with what I'm thinking. Because otherwise other people have already discovered it. Well, that was not the case. So I'm a lucky guy that I picked a subject in which there was very little known, and there was also initially very little interest in it. And there were these big gaps in knowledge which I helped fill.
I can't understand the question.
Yeah, well, I must say at the moment I'm more interested, and this is the subject of my talk this evening before correspondent one. I'm more interested in things happening in the troposphere, and especially in Asia. I can't help it, but you come here to this wonderful country. I've been in Chiang Mai, and whenever you open the window in the morning, in the dry season, in the countryside, in Chiang Mai, we smelled the air. There was smoke in the air everywhere. So that's air pollution, created by farmers in the countryside. It turns out that this simple, you almost might think this is all natural pollution, but no, it's not. It's human pollution, and it is the pollution, you can say, almost of the poor people. Poor people doing agriculture, growing crops. What they do is in the dry season they burn them, and this is happening all over in the tropics and subtropics in many poor countries. And for many gases, and also especially for particulate matter, the emissions of these gases in the atmosphere are even greater than what you get from industrial processes, in the case of many trace gases. And this has the potential for climatic changes, and this is something which I consider to be very important, and that is why I'm involved in studies of this kind. We are building up towards that in the so-called ABC program, that is the atmospheric ground cloud program, or originally called the Asian ground cloud program, because we want to understand what these emissions, bad air quality, bad visibility does to the climate, especially the tropics and subtropics, but also global climate. Now, about that I will speak more.
How to create question that bring to this problem that is useful for mankind.
Yeah, I mean, this is how you discover new things. I don't know. My mind is basically always busy with playing subconsciously with science. It's part of that. And then in the most unexpected circumstances, you start thinking about something. Like while preparing for this evening's lecture this morning, I got a thought and a question. I will find a colleague who is interested in my question, and together we will work on further developing them. So I mean, you cannot predict as a scientist whether you make any new discovery. This is something which suddenly comes. And, whoever has made discoveries can confirm that it's very typical. You just don't sit down and say, I'm going to solve that problem and do it in 20 hours or 20 weeks. No, it may take years, or it may take a few minutes. We don't know. Our brain is unpredictable in that sense.
This one is very interesting. Why can't ozone from somewhere else be after home?
Okay. So can we bring some of too much ozone down at the Earth's surface? How can we bring that into the stratosphere? Well, in some way this happens, because there's always communication between stratosphere and troposphere by transport. But actually it's not a very important process. There is, in fact, it's impossible to create ozone in the stratosphere in the areas where we have ozone depletion, because it will be broken down as quickly as it is formed, because these reactions which break down ozone are very rapid. Now, even if you would increase the amount of ozone in the stratosphere, which would be a very expensive process, but you have to photonize molecular oxygen to make all atoms and then ozone. Even if you do that, you may create problems, because we don't want too much ozone. stratosphere either. We go away from natural conditions. So it's very dangerous to start manipulating with the stratosphere. There have been many proposals to make additional ozone in the stratosphere. And all these proposals I've seen so far have either been totally ridiculous or far too expensive, totally unpractical. There have been indeed a proposal made that airplanes should go up in the stratosphere, filled with ozone, and then released in the stratosphere. Well, it's totally impossible because that airplane which would go up in the stratosphere would explode. Because after all, ozone is a rather explosive gas, so whether it had to do with ozone in the laboratory knows one has to be very careful. But you get such proposal made by the people. So far, every proposal that way has been totally unpractical.
Before I read the last question, I invite the person who would like to ask directly to Professor Crutzen. He's on the microphone. Please identify yourself and ask the question.
I wanted to, as it's your birthday tomorrow, your 71st birthday, we wanted to know what's one thing in the world that you want everyone in the world to follow you on through this scientific research?
It's so difficult to understand, sorry.
Like, it's your birthday tomorrow, right?
Can you speak a little lower because then you don't get this.
Oh, I'm
sorry for that. Yeah.
Like, what's one thing in the world that you want, like, everyone to follow you on through this scientific research?
Maybe you can come forward and then I'm very sorry. Was somebody understood the question?
Closer to the Professor Crutzen in the front.
Hello. His watch got an eye, so I'm gonna help him. Since tomorrow is your birthday, we were wondering, what would you like the most for people to achieve from your scientific achievement?
Do
you understand that?
but I would like to forward to advice.
Yeah.
Scientific. I think considering this university and also the departments which work on the environment, I think the tropical and subtropical world is by far the least studied with regard to its physical and chemical properties and its impact on human activities. My feeling is that the future of climate and also air pollution in the future will be very much determined by what is going to happen in Asia. Asia is firstly, already now, there are more people living in Asia than in the rest of the world. And that ratio is going to increase. And you are, in many ways, developing very quickly technology. So I think this is the region of the atmosphere and the Earth, which has to be studied much more than has been the case now. And this came up in a discussion yesterday. This is not applied research, this is basic research. We collect basic data about physics and chemistry of the atmosphere of Asia, but also in other parts like South America, Africa, Europe, and America. But in the first place, the tropical and subtropical countries. So I hope very much that your university and other universities in these areas take this research very seriously, because let's call it the climatic future of mankind is dependent on what's going to happen in the Asian region.
And the last question. Is there any connection between ozone depletion and climate change?
There is a limited connection. I indicated that, but it goes the other way around. increasing greenhouse gases, and especially carbon dioxide in the atmosphere, implies warming of the Earth's surfaces, so the greenhouse effect, as we know, but cooling of the atmosphere in the lower stratosphere. And because of that, the two things are connected but in opposite ways. So by adding carbon dioxide to the atmosphere, you will change climate, will get warmer. At the same time, the recovery of ozone from all this depletion episode will be delayed. So it hits two ways and in bad ways.
Life, the atmosphere is unbelievable, even late in the afternoon. We are deeply appreciate the greatest honor receiving from Nobel Laureate for chemistry, Professor Crutzen, who have had incredible experience and success. Besides that, he also have master keys of life. We would like to show our appreciation, so may I have the honor to invite Advisor of the President, Chulalongkorn University for Research and Development, Associate Professor Dr. Crutzen, to present a token of our appreciation to Professor Crutzen. Please, Dr. Crutzen.
Thank you, Uwe.
ขอบคุณมากค่ะขออนุญาตเป็นภาษาไทยก่อนนะคะขอบคุณสำหรับความสนใจอย่างยิ่งขออนุญาตประชาสัมพันธ์นะคะว่าสำหรับท่านที่สนใจที่จะรับฟังเรื่องของ air pollution มลพิษทางอากาศขอได้รับการเรียนเชิญนะคะที่จะไปฟังเรื่องของ air pollution in Asia and its impact on regional and global climate. This is evening talk and dialogue at the Foreign Correspondents Club of Thailand, Penthouse Mania Center next to Sogo, 24th Street from Chitlong BTS station. เย็นวันนี้นะคะเป็นเวลา6 โมงจะมีการบรรยายเกี่ยวกับเรื่องของมลพิษทางอากาศที่สมาคมผู้สื่อข่าวต่างประเทศเพนท์เฮาส์มานิยาเซ็นเตอร์ถนนเพลินจิตซึ่งทุกท่านสามารถที่จะเข้าไปร่วมรับฟังได้นะคะและขออนุญาตประชาสัมพันธ์ว่าในการบรรยายการแสดงบรรยากาศครั้งต่อไปจะเป็นเรื่องเทคโนโลยีทางด้านเลเซอร์กับสัญญาภาพและสงครามซึ่งนำเสนอโดย Professor Sir Joseph Roger นะคะซึ่งเป็น Professor ทางด้านฟิสิกส์ขอบคุณมากค่ะสำหรับความสนใจกันท่านต่อไปนะคะวันที่2 มกราคมรวบตัวสบายเลยเราไปแลกมาถึงเราได้ไปแลกครับ อย่างดียิ่งขออนุญาตประชาสัมพันธ์นะคะว่าสำหรับท่านที่สนใจที่จะรับฟังเรื่องของ air pollution มลพิษทางอากาศขอได้รับการเรียนเชิญนะคะที่จะไปฟังเรื่องของ air pollution in Asia and its impact on regional and global climate. This is evening talk and dialogue at the Foreign Correspondents Club of Thailand, Penthouse Mania Center next to Soho, 24th Street from Chitlong BTS Station. เย็นวันนี้นะคะเป็นเวลา6 โมงจะมีการบรรยายเกี่ยวกับเรื่องของมลพิษทางอากาศที่สมาคมผู้สื่อข่าวต่างประเทศเทนทอมณียาเซ็นเตอร์ถนนเพลินจิตซึ่งทุกท่านสามารถที่จะเข้าไปร่วมรับฟังได้นะคะและขออนุญาตประชาสัมพันธ์ว่าในการบรรยายการแสดงปฐกถาครั้งต่อไปจะเป็นเรื่องเทคโนโลยีทางด้านเลเซอร์กับสันติภาพและสงครามซึ่งนำเสนอโดย Professor Sir Joseph Rodriguez นะคะ